a traffic light is an amazing example of a discrete system. A traffic light has three distinct values, right? It can be red, it can be yellow, or it can be green, okay? And I can write this as a set, which are for these three objects, just red, yellow, green, okay? It also already kind of has a function defined on it, right? It has a natural relationship between the elements of our domain, right? It starts out red, and then it goes, oh my gosh, you guys, seriously, I hate driving. Okay, it starts out red, and then it goes to green, and then it goes to yellow, and then it goes to red. Oh my gosh. Well, at least I got it right down here. I swear I drove today. Okay, so why don't we let this relationship between our functions stand for follower, like one follows the other. So what follows red is green. What follows green is yellow. And what follows yellow is red. And then it goes back down to green, right? We have this cyclical relationship. We can draw a graph of this function using arrows that we call edges. Edges denote a relationship or a flow between the two values. And dots, which we call vertices, and the vertices represent all the elements in our domain. So we've got red, yellow, green, so we're going to have three vertices. So let's go red, yellow, green. Each edge connects two vertices. This doesn't necessarily have to be different vertices, and I'll show you that in a second. The edges are said to be incident on the vertices, so they act on the vertices. And if a graph contains one or more one-way edges, we call the graph a directed graph or a guide graph. So some things don't go both ways, like the light doesn't go from red to green and then from green back to red. No, it has to go to yellow and then to red first. So here would be a graphical representation of our traffic light function. So we can represent discrete functions as this type of graph, okay? It's important to note, and I'll show us on the next slide, I believe, that this graph represents a 3-cycle. So the type of loops that graphs create, if they create root loops, which they don't have to, is called its cycle. So a 1-cycle is when an element maps back to itself. A 2-cycle is when it goes between two vertices. Ours was an example of a 3-cycle. Here's a traffic light. And here's an example of a 4-cycle and a 5-cycle graph. So let's work through some examples of functions. So let's graph the function g from the domain to its target, where our domain and our target are I. Remember, I equals the square root of -1. So I squared is -1. Negative I, 1, and -1. This set is sometimes called the quaternions. It was one of my favorite things that we studied in abstract algebra, which is like a course I could teach after this, but I should probably teach statistics, just saying. So, and let's let g of x be I times x. So let's work through what this graph looks like. And I'm going to have to do that by substituting the values of my domain into my function to figure out where they map to. So if I have g of I equals I times I times I is I squared, which is -1. So I maps to -1. If I have g of -I, that gives me I times -I, which is -I squared, which is the negative of -1, which is +1. If I have g of 1, that's going to be I times 1, which is just I. And if I have g of -1, that's going to be I times -1, which is just -I. So I'm going to go ahead and represent each of my vertices with a dot. So I have first that, let's change colors, I goes to -1, so I'll have I. We'll have it go to -1. Cool. Then I have that -I goes to +1, so let's let this be -I and this be +1. Cool. Okay. Then I have that 1 goes to I, so where's 1? Here's 1. I have that 1 goes to I, and then I have that -I goes, -1 goes to I. This isn't a really pretty graph. Let me redraw it. What if I did 1, -I, -1. I have I go to -1, -1 goes to -I, -I goes to +1, and +1 goes to I. So this is a little bit better way for us to see that this graph is a 4 cycle, okay? But I also want you to know that no matter how you draw the graphs, these two graphs are equivalent. So they're the same. It's just this second graph here makes things a little bit easier to see what's going on visually. So if you draw a graph and you don't like how you placed your vertices, you can move them, right? They're equivalent, and this allows us to better see what's going on with our graph. Next, we're going to graph the function g from our domain to the target. We're still working with the quaternions, but this time my function is x squared. So if I take g of I, so I'm substituting in my domain values, I squared is going to give me -1. If I have g of -I squared, that's going to give me I squared, which is -1, because 2 negatives make a positive. If I have g of 1, that's going to give me 1. And if I have g of -1, that's going to give me a +1. So here I have that I've got I goes to -1. I have -I goes to -1. I have that 1 goes to 1, so it maps to itself. And I also have that -1 goes to 1. So here is what my function looks like. Now this isn't as nice, right? This isn't fully connected, and that's okay. It doesn't form a cycle is what I mean, and that's okay. Next, what if I graph the function d to t, where d is 0, 1, 2, 3, 4, and t, our target, is a, b, c. And I have it defined where each element maps to. When the domain and the target are different sets, we set the domain on the left and the target on the right. So first I have that 0, 1, 2, well, maybe I'll do it this way as I go along, so I can keep things a little more organized. So at first I have that 0 goes to A. Then I have that 1 goes to C. Then I have that 2 goes to A. And then I have that 3 goes to B. See how this is still a function? Each unique domain value has exactly one target value.